Welcome to another video. So today we're going to start having a look at the topic of quadratics. So it's going to be the start of chapter 2 in the blue Algebra Year 12 book, and much of this we're hoping will be familiar to you from GCSE level, but as we get deeper and deeper into the chapter, some of the concepts probably won't have been introduced in such depth before. So some of this being familiar should hopefully give you a bit of a head start and some confidence to take it further. Before we go into the topic of quadratics as such though, the new stuff, I want you to have a look at these warm-up questions, which we always have, questions 1 to 4. Try them by yourself first, and then only check my solutions after. That way you'll get the full benefit of trying them yourselves without just copying down an answer. So let's start off then together by working through question 1. So question 1, we've got two sets of linear equations to solve. So first of all, for part A, let's just leave 7x minus 5 as it is. And as you'd be very familiar with, if you see brackets, usually it's a good idea to expand them. So 3 times x gives us 3x, and then 3 times 5 is 15. Then bring all the x's onto one side, all the constant numbers onto the other. So we can subtract 3x from both sides first, which gives us 4x minus 5 equals 15. Add 5 to both sides, that gives us 4x equals 20. Finally, when we divide by 4, we'll see that x is equal to 5. For part B, again in a similar way, just expand the brackets out to begin with. So 6 times x gives us 6x, and 6 times minus 4 is minus 24. And that's going to equal 2 times 2x, which is 4x, plus 2 multiplied by 3, which is 6. Once again, bring all the variables to one side, so get all the x's together. We can do this by subtracting 4x from both sides. That would give us 2x minus 24 equals 6. Add 24 to both sides, gives us 2x equals 30. And if 2x is equals 30, it stands to reason when we divide by 2 that 1x equals 15. And so that's question 1 sorted out. Question 2, we've got some quadratics to factorise. Now, this should be nothing new or nothing scary, we're hoping, from what you've seen before at GCSE level. And so, for the first one, for part A, we just need to find two values, which when we multiply them together gives us 18, and when we add them is 19. Well, that's hopefully fairly obviously going to be 18 and 1. So that's going to become x plus 18, x plus 1. 18 multiplied by 1 is 18, 18 add 1 is 19. Exactly the same idea for B, no different at all, only now we've got negatives to deal with. So we need to find two numbers, which when we multiply them together gives us negative 35, and when we add them that gives us negative 2. And so the numbers, hopefully you'll find out, are positive 5 and negative 7. So in either order, one bracket is x plus 5, and the other bracket is x minus 7. Question 3 of a warm-up, we have a compound shape to calculate the area of. We're told that the area of this compound shape is 7x plus 5 centimetres squared, and we need to find the area of x, which is here. If we take it back to GCSE level and doing compound shapes, the same still applies. A level doesn't actually change any facts, it just adds to them. So what we'd have to do here for the compound shape is to divide it into two easier shapes to calculate. And so we can see from this dashed line that this side is 3, and therefore this side as well must have a length of 3. So we can work out fairly straightforwardly that this section here must be a square that has an area of 9. We can also work out the area, in terms of x at least, of this rectangle on the left-hand side. And so we're told that it's got a width of x, and this length here is 2, this length is 3. And so the total length of this rectangle in its complete form is going to be 2 plus 3. It's going to have a length of 5. And so this rectangular bit of the shape is going to have an area of 5 multiplied by x. In other words, this bit's got an area of 5x. So the whole shape must have an area of 5x plus 9. But from the wording of the question, we're told that the area of the shape is 7x plus 5. And so this 5x plus 9 must be one and the same as 7x plus 5. We can then solve this equation in much the same way as we worked out question 1. So subtract 5x from both sides. We get 9 equals 2x plus 5. And subtract 5 from both sides, we have 4 equals 2x. Divide through by 2, therefore x must be 2. And finally, for the warm-up, question 4, we need to solve the equation 3x squared equals 75 for part A. So for part A, what we can do is we can divide both sides of this by 3. And so when we do that, we're going to get that x squared equals 25. We can then square root both sides, so therefore we have that x equals plus or minus 5, either positive or negative 5, so 2 solutions to this one. For part B, again we can divide both sides by 4, not dividing by 3, but I'm just saying we can divide both sides by a certain number. So here we have x squared minus 20 equals 0. Add 20 to both sides. That's going to give us that x squared equals, whoops, divided the x squared but not the 20. That's a schoolboy mistake. Big apologies. So x squared equals 5. Therefore, in the same way as before, x is going to be plus or minus the square root of this side, so plus or minus the square root of 5. And those are the warm-up questions complete. So now let's march forward and just consolidate some of the stuff we already know on solving quadratics. So let's have a look at question 1, for example. So we've got A, B and C to solve. So let's try and solve these equations together. So first off, like we saw in question 1 of the warm-up, factorising has a certain power. So if we factorise them, if we can factorise of course, sometimes we can't, it makes solving quadratics much, much easier. So here we have x squared minus 7x minus 18 equals 0. Same drill applies. Can we find two values that multiply to give us minus 18, and when we add them, they give us minus 7? Well, of course we can if we think long and hard enough. Those two values are going to be positive 2 and negative 9. So we can say that x plus 2, x minus 9 equals 0. And so we've got one bracket multiplied by another bracket equals 0. And we could call one bracket A and the other bracket equal to B. So if A times B equals 0, that's only going to be true if either A is 0 or B is 0. And so either this bracket is equal to 0. If x plus 2 is equal to 0, that would only be true if x is minus 2. Or the other possibility is if the second bracket is equal to 0. If x minus 9 is equal to 0, then x must be equal to 9. The quick way of doing it, look at the values in the brackets, swap the signs. Plus 2, minus 9, positive. For part B, what we need to do for this one, when we factorise it, is use what I tend to call the AC method. And so I'm just going to write this down here. And then we're going to multiply the coefficient of the x squared by the constant term, the 12. So we've got 2 times negative 12, which is negative 24. That tells us, in order to factorise this one, we're hunting for two numbers which multiply to give us negative 24, and when we add these two numbers, it gives us the 5, as in this 5x. So two values that multiply to minus 24, and when we add them, they give us 5. Those two values are going to be positive 8 and negative 3. So we're going to have 8 and a negative 3. What we now do is we partition the 5x into a positive 8x and a negative 3x. So we rewrite this as 2x squared plus 8x minus 3x minus 12 equals 0. We can now factorise twice. So these two bits here we can factorise into a 2 and an x, which gives us x plus 4 in brackets. These two bits here are both negative and have a common factor of 3, so we can factorise out a negative 3. And again we get the same bracket, which is no coincidence, x plus 4 equals 0. These two bits at the front of the brackets can now form together into their own bracket, so we now have 2x minus 3 brackets x plus 4 equals 0. Now the same idea applies, so either first bracket's equal to 0, in which case x would have to be 3 over 2, so therefore either x equals 3 over 2, or if a second bracket is equal to 0, x would have to be negative 4. Finally, for part C, what we need to do is rearrange this so it's in the standard quadratic form, which is ax squared plus bx plus c equals 0. So one side has to equal 0 when we're factorising a quadratic typically. So we've got 6x squared, 1x here, 2x is here. So if we take away 2x from both sides, we're going to have a minus x. And if we minus 5 from both sides, that's going to give the left-hand side equal to a negative 2 at the end. So that now at least is in the standard form. We couldn't have done anything without this first important step. Now what we're going to do is the same as part B. Using the AC method, we're going to multiply the 6 with this negative 2. 6 times negative 2 is negative 12. And so we're going to hunt for two numbers which, when we multiply them together, give us negative 12, and when we add them together, gives us minus 1, as in this minus 1x. So, what are these two numbers? Does anybody know? Hopefully most of you know that it's going to be 3 and negative 4. So we partition this minus x into a positive 3x and a negative 4x. So that's what we have now. Now we can factorise this bit here. Both have a common factor of 3 and a common factor of x. So we can say this is 3x brackets 2x plus 1. And this bit has a common factor of both minus 2, and that's the same as 2x plus 1 equals 0. These two bits at the front of the brackets form together to make their own bracket, so then we have 3x minus 2, 2x plus 1 equals 0. Then the same logic applies. If this bracket's equal to 0, it works. And so if this bracket is equal to 0, x would have to be 2/3. So either x is equal to 2/3, or x might have a value that makes this bracket equal to 0. If 2x plus 1 is 0, x would have to be negative 1/2. Moving forward, we've got to find the exact solutions to these two equations here. And so for part A, we've got x minus 5 all squared equals 49, and for part B, 2x plus 1 all squared is 17. So for part A, in fact I'll just draw a line to just separate these out, so we're not going to get part A and part B merging into each other in a mess. Here we go. So part A, what we can do is just square root both sides. So square root of x minus 5 all squared is x minus 5. Over here, really importantly, we don't just consider the positive square root, we need to consider both the positive and the negative square root. And so we can't say x minus 5 is 7. What we can say is x minus 5 is either positive 7 or negative 7. So now based on that, we can say that either x is 5 minus 7, which is minus 2, or x is this 5 plus 7, which would be 12. Again, if you substitute minus 2 and 12 into this expression here, you should find that it does give a value of 49. Next up, part B. Similar procedure. We can square root both sides. Square root of something squared is just the thing without the square symbol there at all. And over here, we have the square root of 17. I hope you're screaming at the video now, saying, isn't it plus or minus? Yes, it is. Well done if you're thinking that. Now we can subtract 1 from both sides. So we have 2x equals minus 1, again, plus or minus root 17, like so. Then divide through by 2. We therefore have that x is either equal to minus 1 minus root 17, all of that divided by 2. Or the second option is that x is minus 1 plus root 17 all over 2, like so. Question 3. This is very similar to the warm-up question, but slightly trickier in terms of the algebra needed to solve it. So we've got the shape here, it's got sides shown in centimetres. The area we're told is 51. Find the value of x. So what I'd suggest we notice first of all is if this is a length of x and this has a length of x, we can section off this bit of the shape like so, and we can say that this area here, which must be x multiplied by x, that has to be x squared. And so we can write that down straight away. Whereas this bit here is obviously rectangular, we know its total height is 7, but we don't know yet this width. And so what I'd suggest we do is we think about what this width actually is. So if we go from one end to the other, the whole width, we're told, is 2x minus 3 for the whole shape. This bit here has a width of x, and so if the whole thing is 2x plus 3, and this bit's x, this must be the remaining other x plus 3. And so this width here, I can just add in what it is, x plus 3. This is double check, x plus 3 plus x is 2x plus 3, so it does make sense. So this rectangle is 7 long multiplied by x plus 3 wide, area of a rectangle, length times width, so this area here would have an expression which is 7 brackets x plus 3. So in terms of x, we now know that the area of this shape must be x squared plus 7 lots of x plus 3. But we're also told in this question that this area has to be equal to 51, because it says right here. So we can now expand, manipulate, solve. So x squared, expand out these brackets, 7 times x is 7x, 7 times 3 is 21, so that then equals 51. This isn't in the standard form, we need to subtract off 51 from both sides. If we do that, we're going to get x squared plus 7x minus 30 equals 0. This will now factorise quite nicely. I'm hoping you're starting to think, well, what if it doesn't factorise? What do we do then? This is what we're going to show you later this lesson. So anyway, we need to hunt now for two numbers which multiply together to make minus 30, and when we add them, give us plus 7. There are two numbers that exist that do this for us. One is positive 10. The other is negative 3. So what we have here is either x is equal to minus 10 or x is equal to 3. Just interpreting the algebraic side of things only. So either x is minus 10 or x is 3. That seems to make sense. However, just go back and think, what on earth actually, in the context of this question, is x? It's not anything abstract, it's actually something which relates to geometry. It's the length of the side. Because x is a length, can we have x being negative 10? Obviously, no, we can't. And so what we do is we need to reject, with good reason, this solution. So we're therefore left with the fact that x must be equal to 3. It might be a one-mark question in an exam, where the examiner asks, why can't x be negative 10, or why is there only one solution? An answer to that could be, x is a physical length, so cannot be negative. So, that's these sections done. We're going to move on now, in a moment, to the idea of completing the square. So here we are, completing the square. You will have heard of this. I'm hoping, in fact, you're already very familiar with this idea from GCSE. What you might not have been told, and actually what I wasn't told when I was a student, is why is it about completing the square in terms of geometrically? What's it got to do with a square? It's got to do with squaring things and square rooting them, but is there any geometric relationship? And there absolutely is. So this is what we're going to try and illustrate before giving you the hard, fast rules on how to complete the square. So for example 1, we've got this sequence, this diagram, and we're asked, how does this sequence below help us to solve the equation x squared plus 6x equals 91? You've got the full solution, the full sequence in your notes. I'm just going to do this step by step so I can talk you through it. So this area here, the red is x squared, the yellow is x multiplied by 6, which is the 6x. So for the first step, we can imagine now just dividing this into 2, the yellow bit. And so one bit's 3x, the other bit's 3x. Next, we can take one bit of this yellow, just saying here it's 3, take one bit of that and move it to the side. And so that is almost a square, you can see. The only thing that's missing is this bit. And so we've got x squared plus 3x plus 3x. So as I say, this is an incomplete square, and this dotted section here represents the incomplete part of the square. So what we can do, you might be able to guess how we can go from an incomplete square, what the next step might be. What we're going to do now, pardon me, is we're going to complete the square. And so what's missing here? Well, if this length is 3 and this width is 3, this little square, what's missing, must have an area of 9. And so we just pop this in now, and then we've got a complete big square. And so it's x plus 3 long, x plus 3 high. So we can use this completed square idea to solve this equation. So next up, how does that help us to solve x squared plus 6x equals 91? Well, what we can do here is we can now rewrite x squared plus 6x in this completed square form. And so x squared plus 6x is actually almost the same as x plus 3 squared. X plus 3 squared is all of this. You might be thinking, why did you say almost? Well, this 9 isn't actually a part of the original expression. And so this is the complete square, but then we have to remember this 9 actually wasn't there. So what we have to do is take away that 9 and just get rid of it altogether. Okay, so we then take away that 9 literally, and then we have what we need to have. And so x squared plus 6x is the same as this thing here. And so that is equal to 91. If we add 9 to both sides, we get that x plus 3 all squared must be 100. Square root both sides tells us that x plus 3 is plus or minus the square root of 100, which is plus or minus 10. Now here, this sequence is just to sort of give a visual representation of why completing the square works. So you don't have to actually stick to that like glue. We don't need to rigidly say that because this is a diagram, x must be a length. If it did say in the question, this is like a field or a garden or something, then we would have to reject any negative answer. But for now, just try and marry up the abstract with the concrete. So let's leave in this minus 10 just to generalize any full solution. So we're nearly there in terms of solving it. All we need to do is subtract 3 from both sides. So either x is negative 3 minus 10, which should be negative 13, or it could be that x is minus 3 plus 10, which should be positive 7. I have another example for you here. So here's another diagram, different sequence. So how does this sequence below help us to solve x squared plus 4x equals 28? So like we did before, we take the 4x and we half it, we split it in two, like so. Once we've split it into two, we keep one section here, move the other section to the other side. This now is an incomplete square. As you can see, that's missing. And so what we need to do is complete it in a moment. This one here has to be completed with a little square of area 4, because this one's 2, and that bit's 2 as well. 2 times 2, we've got a missing bit, which is 4. So that's the incomplete square. This is completing the square. And so what we can do now is rewrite the x squared plus 4x part of this in terms of this completed the square form. This whole square, including the 4, has an area of x plus 2 multiplied by x plus 2. And so this thing here we can write as x plus 2 all squared. However, by doing that, it includes this 4, which strictly speaking was never there in the first place. We just used this 4 to complete the square. And so we need to remember to get rid of this 4 and totally wipe it off. And so to get rid of something mathematically, we subtract. So we need to minus off that 4. So what we're saying is x squared plus 4x is the same as this here. And we're told that equals 28, so we can just fill that in. So we therefore have x plus 2 all squared. Add 4 to both sides, that's 32. Square root both sides, so x plus 2 must be plus or minus the square root of 32. Now, if you remember back to the previous chapter, can that surd be simplified? Is there any factor of 32 that's also a square number? Yes, there's a few actually. The biggest factor of 32 that's a square number is 16. So we can rewrite this as being plus or minus root 16, which is 4, plus or minus root 2. So root 32 is the same as 4 root 2. So therefore, when we subtract 2 from both sides, we can say that x is either going to be minus 2 minus 4 root 2, or that x is minus 2 plus 4 root 2. And so that's just a visual representation of why completing the square works. Next up, without using those diagrams, let's have a go at writing these expressions in completed the square form. Before we do that though, I did promise you the hard and fast way of doing it. So what we have here is an x squared typically, and then a certain amount of x's are tagged on. And so the general idea is if we have an expression of the form x squared plus, let's say, bx, what we do, and what we did in those diagrams, is we halved the coefficient of the x. So we literally divided the section into 2. And so what we need to do is we put in the brackets, instead of x squared, just an x, and then the b we just divide by 2. So whatever the number in front of the x is, we divide it by 2 and square that whole thing. That's the completed square form. But remember, we then needed to subtract that value, which made the little square in the top right of our diagrams. So generally speaking, the area of that little square we need to then subtract off is this b over 2 all squared. Okay, and so that's the general thing we need to remember how to do. That's our recipe for completing the square. So for part A, our b for part A is actually 6. Okay, so I'm not saying you need to use this recipe, as it were, this formula all the time. In fact, the quicker you can move away from this, the better. Just try and assimilate this into your long-term memory. But I'll just show you how this works and the fact it does work, and you can check in your calculator after if you'd like. I'm deliberately not really referring to the class words right now because I want to just work on the standard skills from GCSE and the non-calculator algebraic manipulation, which will be so important for later in this year and year 13. So if you're wondering why I'm not just typing numbers into the calculator really quickly, I'm trying to push for understanding with these videos. So here we have plus 6. So what we do is we put into brackets the x and half of that 6. Square it. Then we minus off that half of the 6, which is 3, all squared. So we minus off whatever's in this end bit of the bracket squared. 3 squared is 9. So it's as simple as that. For part B, in the bracket we put 1x and half of the coefficient of this x here. Half of 4 is 2. Square that. When we minus off the 2 squared, so we minus off 4. Now let's work through some increasingly harder problems on completing the square, so we've become proficient and really skilled with doing this. And so write each one of these in completed square form. So for part A we have x squared plus 5x. Like I mentioned before, we put into the brackets the x. We half the coefficient of the x here, so half of 5 is 5 over 2. All of that squared. Then we subtract off 5 over 2 all squared, which is 25 over 4. For B, same idea. So into brackets we put the x, and this minus 3 we half, so we put minus 3 over 2 squared, and then we subtract off minus 3 over 2 all squared. So even if this term, the second term in the bracket, is a negative, remember when you square a negative it turns out to be a positive. And so this all squared is 9 over 4, so we subtract off the 9 over 4. For C, slightly more complicated. The trick here is we're only focusing on this bit when we complete the square. We ignore the constant term and include that only afterwards when we're simplifying. And so the x squared minus 8x, that just becomes x minus 4 all squared, and then we minus off the minus 4 all squared. Minus 4 all squared is 16, so we minus off 16. Then remember to include this plus 5 at the end. So that becomes x minus 4 all squared, and minus 16 plus 5 becomes overall minus 11. Last couple of examples. And so the wording here is just what you might see similar in some sort of exam. It's exactly the same idea as what we've done. However, what we're seeing here is that we don't have just 1x squared. So I need to mention how to do these to you. So if you've got a coefficient of x squared which is non-unitary, not just 1, we need to factorise out whatever coefficient we have of x squared before we do anything else. So I'm just going to section off the A and the B, again to just make sure we don't collide and it reads in a nice clear way. So if I just put this down here like so. So what we need to do is factorise out this 2 first and foremost. Now because when we complete the square we have brackets anyway, what I tend to do is to include big square brackets, just to not get confused with the main completed square brackets. So first of all I'm just going to take 2x squared minus 12x and factorise out this 2. So I'm going to say it's equal to minus 2 and big brackets like this, x squared minus 6x. Now what we can do, we can ignore this 2 until the end steps, just focusing on completing the square for the x squared minus 6x, because now we have just one x squared. We have now something which is more familiar to us. So like I say, leave the 2 alone and complete the square on x squared minus 6x. So we take the x squared, just pop 1x into the brackets. We half the minus 6, so it becomes minus 3, and we square that. Then we subtract off this term here all squared. This here all squared is 9, so we subtract off the 9. So just to be perfectly clear, we'll leave that 2 we factorised at the beginning alone. We're just working on completing the square of this. We're not bothered about this 2 at all until the last step, which is now. So now we can expand this out. So we've got this bracket here all squared, 2 lots of that. And then 2 lots of this minus 9, which is minus 18. Over here, exactly the same idea. And again, we leave any constant term alone. So first of all, we're just looking at this part here. So for part B, we're going to complete the square on 3x squared plus 6x plus 1. So again, we're going to factorise out whatever coefficient we have of x squared. So we're going to take this 3, factorise it out, and put some big curly brackets in like so. Sorry, big square brackets. So factorise out a 3 from the x squared and the 6x bit. We have x squared plus 2x inside of these big curly brackets. Again with that plus 1 tagged on the end, which we're not going to bother with yet. So we have 3 big square brackets. Now we just complete the square on this x squared plus 2x part. And so x squared becomes x in the brackets. Half of 2 is 1. We square all that, and then minus off this thing squared. The square of 1 is 1 times 1, which is 1, which is why we minus off for 1 like so. Finally, that plus 1 at the end. It's only now at the last step we bother with this 3 we factorised out at the beginning, and this plus 1 at the end. So expand out all of this, multiply all this by 3, we get 3 lots of x plus 1 all squared. 3 times minus 1 is minus 3. Again with this plus 1, which we can't forget about. So overall we have 3 lots of x plus 1 all squared. Minus 3 plus 1, that gives us minus 2. So quite a lot to get your head round in that lesson, which is why it's so important for you to try these. So on 2A, I want you to try these sections of question 1 and question 2, and then questions 3, 4 and 5. After trying that, turn to page 23, exercise 2-3, try these sections of 1, 2 and 3 before having a go at question 4. It is so important you try these yourselves. Just passively completing the notes will get you so far, but not far enough. Try those now, please. Check your answers at the back after you've tried each couple of questions. Don't do loads of questions and then check at the end. Regularly self-assess. If you've made a mistake, correct your mistakes. If you're not sure where you've gone wrong, ask me either in lesson, on an email, or in the comment section of these videos. Once again, I thank you very much for listening. Cheers for getting to the end of the video, and you'll hear from me again soon, I promise. Take care. I'll see you soon.